Alright, so chapter 11, number 14 is the first problem I'll do, and that's a fun little problem that uses conservation of energy. And what's important in this chapter is that with kinetic energy, um, we have both rolling kinetic energy and translational kinetic energy. So this problem will demonstrate both of those. So we get a ball here, and it starts with some kinetic energy, both rolling and translational, and it goes up this ramp and then off this little cliff, and projectile motion lands a distance d away. The height from here to here they call h1, and this height here they call h2. And we need to find the initial speed down here, v initial. Alright, so let's just put some numbers to these. D equals 0.06 meters. They give it in centimeters in the book. I just converted. H1, oh, H1 is 0.05 meters. H2 is 0.016 meters. Alright, so first off, the speed of the ball is going to decrease on the way up. It has to, because the kinetic energy is turning into gravitational potential. And so, so we're going to have KE rolling down here plus KE linear, I'll call it. It could be translational as well. That's going to turn into gravitational potential plus, I should put initial here, initial plus KE rotational final plus KE linear final. And that is going to give us our initial speed as a variable here. Everything else we know, or we will find out from projectile motion. So let's just write this out. This becomes 1/2 m. Now this is actually the rotational. Let me do that in the correct order. One half I omega initial squared plus 1/2 m v initial squared. That's going to turn into mgh plus 1/2 I omega final squared plus 1/2 m v final squared. And this is a solid sphere, so that's going to be, we can expand this, 1/2 solid sphere is 2/5 mr squared, so 2/5 mr squared. Omega is v squared, v over r, so this becomes v squared, v initial squared over r squared, plus 1/2 m v initial squared. That's going to equal mgh plus 1/2, still 2/5 mr squared. Now it's v final squared over r squared plus 1/2 mv final squared. M's cancel. These two cancel. All the m's cancel. These twos cancel. These r squareds cancel. That's nice. So we really got 1/5 vi squared plus 1/2 vi squared. And that simplifies to 7/10 vi squared equals gh from here, and then again 1/5 plus 1/2 is 7/10. 7/10 v final squared. Alright, so we know g, we know h. We can figure out v final squared easily through projectile motion. So let's do that right now. So our x direction, we got delta x, we got vx, we got t, and in the y direction we got v initial y, v final y, a, t, the good old days of projectile motion. So in the x direction it goes d 0.06 meters. Well, we need this. This is vf over here, up here. Delta y, it drops down h2, so that's 0.016 meters. Starts off at rest because it's launched horizontally. That's nice. 0 meters per second. Through your experience, you hopefully are comfortable with not needing to know this at this point. And we're calling down positive, so we said this is positive 0.016, so this is positive 9.8 meters per second squared. With this we can figure out t using delta y equals v initial y t plus 1/2 a t squared, 0.016. That's 0, v initial 0, woohoo! 1/2 9.8 t squared. Solve for t and you get 0.057143 seconds. That t is also here, same t in both directions. So then v final equals delta x over t, which is 0.06 over 0.057143. That equals 1.05 meters per second. So you take that 1.05, stick it up into here, solve for v initial. I'll skip all the algebra, you can do that. You get v initial equals 1.34 meters per second. Cool. And that's it.